This lecture will introduce you to probability theory. So turn to page about 103 in the course packet where you see the probability terms slide. There are many situations in business and marketing where we don't know what's going to happen. Now, often we can assess the likelihood that something will happen, but we don't know for sure whether or not it's going to happen. And if we combine these likelihood figures of whether or not something might happen along with costs and revenues, we're going to be able to make better decisions. So for example, if I expose somebody to a banner ad, I'm not really sure what's going to happen. Either the person clicks on it or doesn't click on it. But if I knew something about the likelihood that that person would click on it, as well as, for example, what the expected revenue I get if the person would click on it, and if I knew about the costs of having that exposure, then I could make an informed decision about whether or not I should buy that banner ad, buy the exposure of the banner ad. Okay, so we're going to be learning a set of rules that will enable us to combine probabilities and information about expected costs and revenues in various ways to make better decisions. So random experiments fundamentally, probability theory focuses on something called a random experiment. So a random experiment is any well-defined procedure where we don't know what's going to happen. So there's a well-defined procedure, but something's going to happen. We're not quite sure what it is. So the classic example of a random experiment is flipping a coin. So the well-defined procedure is I take a coin out of my pocket, I throw it up in the air, and I don't know what's going to happen. If I were to roll a die, that would be another example of a random experiment. I expose somebody on the New York Times web page to a banner ad. Well, I don't know what's going to happen. Either the person clicks on it or not. So these are all examples of random experiments. Random experiments will result in some outcome. So an outcome is just the result of a random experiment. For example, if I were to roll a die and it comes up heads, well, getting heads is an outcome. If somebody clicks on the banner ad, well, clicking is an outcome. If I ask you, how many times did you go to an art museum last year, and you say you went 2 times, that's an outcome. Another term that you'll need to know is sample space. So the sample space consists of all possible outcomes of a random experiment. Let's consider the example of me flipping a coin. Well, the 2 possible outcomes are heads and tails. If I roll a die, there are 6 possible outcomes, 1 through 6. If I expose someone to a banner ad, the 2 possible outcomes would be click or not click. Now, usually we don't care about individual outcomes, and instead we care about collections of outcomes. Now, these collections of outcomes are called events. So if I ask somebody, how many times did you go to an art museum last year? Maybe I only care about whether that person is a heavy user of art museums, which is defined as being those who attend 2 or more times per year. Likewise, if I roll a die, maybe I only care about even results. I don't care about the odd ones. In that case, the event would be composed of the numbers 2, 4, and 6. Now, probabilities tell us in loose terms how likely some event is to occur. And there are a number of ways that we can arrive at these probabilities. So one approach is called relative frequency. And with relative frequency, what you do is you just execute the random experiment many, many times and observe the fraction of times that that event occurs. So if I take out a coin and I flip it 1,000,000 times, and if I observe, say, 500,000 heads, I would estimate the relative frequency of a head would be, 50%. That would be my best estimate of the probability of a head. Or if I were to buy, 100,000 exposures of some banner ad and observe the number of clicks, well, that click-through rate would then be my estimate of my relative frequency estimate of the probability of a click. Very often, though, you're not going to be able to do this. So you're not going to be able to replicate something, 1,000,000 times and count the number of times it occurs. In that case, what we often do is make a subjective estimate. So if we think about what's the probability that Northwestern will win its game this weekend, well, there's no way for us to replicate this experiment a million times. These two teams are only going to meet once in this manner. If we had them play a bunch of times, well, they would be different than this time. Anyway, we couldn't have that happen. So the only way we can assess whether or not Northwestern's going to win the game is to make a subjective estimate of that. So we would have some expert who knows a lot about basketball and would know a lot about the opponent and the conditions under which this game are going to be played, and who has an injury and all those sorts of things. And after taking all these factors into consideration, that expert is going to give us a subjective probability estimate. A third type of probability estimate is called theoretical, and we will be deriving some probability estimates based on a model in the next chapter. Let me just give you a simple example of this. So theoretical probabilities are arrived at through a set of assumptions. So let's just take a very simple situation like rolling a die, and I'm going to make the assumption that every side of that die is equally likely to come up. All right, so if I make that assumption, that implies that the probability that I get a 3, for example, is going to be 1 over 6, 1/6. Okay, so the point is we have some assumptions, and these assumptions imply some probabilities. So it's not an empirical thing, it's not a subjective thing, it's based on some mathematical model. Finally, a few words on notation. We're going to be studying probability events, and so we're going to use capital letters to denote an event. So for example, a capital A will make a very nice name for an event. And then we're going to refer to the probability of A as P at A, P parenthesis A. A few technical facts about probabilities. They're always between 0 and 1. Can't have a probability greater than 1. Can't have probabilities that are negative. And if you add up all the probabilities of all possible outcomes, they'll sum to 1. So they have to add up to 1. You have to cover everything. Let's now move on and do a couple example problems. So what I would recommend you do is pause the video right now, read through the problem, and then answer them. So why don't you pause it right now, and then I'll give you the answers. Okay, so now that you've paused it and you've written down the answers, here are the answers. So describe the random experiment in problem 1. Well, the brokerage house Ford is going to somehow let everybody know what its earnings were. And I don't know exactly how they do this, but there's some well-defined procedure where they let people know what happened. So perhaps they release a press release saying our earnings were such and such, or perhaps they have a press conference where somebody walks up to a podium and says our earnings were such and such. So that is the well-defined procedure that makes the random experiment. What is the sample space? Well, it can be anything, right? Any real number could be their earnings. So the sample space includes all real numbers. What does this outcome tell you? Well, it tells you their earnings for the previous quarter. Let's look at part D. Based on everything you currently know, we've computed an expected dollar figure for the expected earnings. So let's just say, for the sake of argument, that we think the earnings will be $50 million. So identify precisely the event announced earnings are higher than expected by listing the qualifying outcomes from the sample space. Well, this event would be all numbers greater than $50 million. So we think it's going to be $50 million. Anything greater than $50 million makes up that event that the announced earnings are higher than expected. Why don't you try problem 2 now? Pause the video and do number 2. Okay, welcome back. So what's the random experiment described here? Well, we're going to find out how many seat covers were produced today. So perhaps I look at an email from my supervisor and it says we made however many seat covers we made. That's the well-defined procedure through which I find out how many we produced. What's the sample space? Well, the sample space are going to be all the counting numbers. So 0, 1, 2, 3, 4, ... What does the outcome tell you? Number of seat covers. Identify precisely the event produced within plus or minus 5 of the daily goal of 750? Well, this event is going to be composed of 745, 746, 747, all the way through 755. Part E. In 8 of the past 15 days, this event has occurred. Find the appropriate relative frequency. Don't make this harder than it is. 8/15 is the answer. That's probably good enough for these. Let's now move on. Now I'm going to give you a few more terms and some basic results from probability theory. So let's say for this entire slide that A and B are some events. The first term I'm going to introduce is called complementary events. So I'm going to go over to PowerPoint where I've sketched out a few graphs, Venn diagrams. And usually we use Venn diagrams to represent the sample space. So this big oval is the sample space. Recall that if you add up the probabilities of all possible events or all possible outcomes within that sample space, the area is going to be 1. So think of the area of this thing as being 1. Now, some subset of the sample space is going to be event A. So let's just say this slice off to the left is event A. Everything that is not in A is called the complement of A. So the stuff off to the right is labeled not A. Now the complementary rule says that if we want to find the probability that it's not an A, we just take 1 minus the probability of A, and that ought to be somewhat intuitive in that the area of the entire sample space is 1, and everything that's not an A is not A. All right, so that's the complementary rule. One other thing about the notation. So if we go back here, there's a couple different notations that are used. If you want to say not A, that's perfectly legitimate. The notation that you'll probably see a little bit more often than that is just A with a line over the top. And that A with a line over the top is not A. Sometimes you'll see something like A with superscript C on it. All right, the next term that I want to introduce is mutually exclusive. Let's go back to the PowerPoint now. Mutually exclusive events are events that cannot occur together. So when one event occurs, the other one cannot occur. So let's think about rolling a die. The event that I get a 3 when I roll that die, and the event that I get a 4, those events are mutually exclusive because me getting a 3 precludes me from getting a 4. So in my Venn diagram, notice how A and B have no overlap, indicating that they cannot occur together. Now something that's really important to note is that when you have mutually exclusive events, the probability that they occur together is 0, indicating there's no overlap.